Now I will talk about the definition of a statement. A statement is a declarative sentence that is either true or false, but not both. It cannot be ambiguous, it cannot be a question, and it cannot be an opinion. In logic, we are only interested in sentences where a definitive truth value can be assigned. For example 1, we have R implies R or S. From the, from the table, we can see this is what we call a tautology. All statements are true for R implies R or S. For example 2, we have R and bracket S and negation R. From what we can see in the table, this is what we call a contradiction. All statements are false for R and bracket S and negation R. And moving on to example 3, we have bracket R implies negation S and negation S. We can see in the diagram. This is contingency because there is some statements that are true and some statements that are false.
To start, what is converse, contrapositive, and inverse? So, for converse, is the result of revising the order of the hypothesis and conclusion of the statement. Um, Other than that, for contrapositive is a logically equivalent statement that is formed by negating and swapping the hypothesis and conclusion of a conditional statement. Last but not least, inverse is a type of conditional statement that is immediate of inference from another conditional sentence. For a small example, P implies Q. For its converse for P implies Q will become Q implies P. And for its contrapositive, for contrapositive for P implies Q, it will become negation Q implies negation P. Last but not least, for inverse, inverse of P implies Q will become negation P implies negation Q. And we can prove um, converse, contrapositive, and inverse all on a truth table such as this. Now let's get into examples. For example, one, the statement said, for the statement, if she is sick, then she takes medicine. For its converse, the statement will become, if she takes medicine, then she is sick. Other than that, for its contrapositive, the statement will change to become, if she does not take medicine, then she is not sick. Last but not least, inverse. For the inverse statement, it will become, if she is not sick, then she does not take medicine. Now we'll get into example 2. The statement is, if the alarm clocks ring, then Fatin will do homework. So we can put the statement into P and Q. So let's we can separate the alarm clock's ring into and put it into P, and Fatin will do homework into Q. And then we can put it into a notation. For example, P implies Q. If the alarm clocks ring, then Fatin will do homework. So let's now get into its converse, inverse, and contrapositive. For its converse, it will flip, P and Q will flip into Q implies P, and the sentence will become, if Fatin do homework, then the alarm clock rings. For inverse, the notation will become negation P implies negation Q. Thus, the statement will become, if the alarm clock does not ring, then Fatin will not do her homework. Last but not least, for it's contrapositive. The notation would flip and it will have negation on both P and Q, so it will become negation Q implies negation P, and the sentence will become, if Fatin does not do homework, then the alarm does not ring. Last but not least, example 3. If Ali is healthy, then he is brilliant and hardworking. So there are 3 points here that we can separate. First, P, Ali is healthy. Q, Ali is brilliant. And R, lastly, Ali is hardworking. And we can put it into a notation which would become P implies Q and R. For the inverse of that statement, the notation will become negation P implies negation Q or negation R. So the statement will become if Ali is not healthy, then he is not brilliant or not hardworking. And then for converse, the notation will flip to become Q and R implies P. And the sentence would become if Ali is brilliant and hardworking, then he is healthy. Last but not least, contrapositive. The notation would also flip like before and would have negation on all PQR. So it will become negation Q implies negation R. Oh, sorry. So it will become negation Q or negation R implies negation P. And the statement will become if Ali is not brilliant or not hardworking, then he is not healthy.
Today, I'm going to share with you about the law of logic. What is the law of logic? The law of logic are basic rules that can help us think and argue clearly. Here, they are in simple terms. First one. First one is the law of identity. The law of identity is the thing what they want for. For example, a chair is a chair and a book is a book. Second one. Second one is a law of non-contradiction. Something that cannot be true and not true at the same time. For example, a door cannot be opened and closed at once. The third one is the law of include neither. Neither for any two statement is might either be true or false. There is no middle option. For example, either the sky is blue and it is not so. This rule help us and make sure our thinking is logical and constant. Okay, next we go to the example. To show negation Q implies P, P and Q is Q. Okay, first one we have to use implication law. Second, we have to use De Morgan law. Next, we have to use double negation law. Next, we have to use communicative law. Then we use justification law. And next we use inverse law to change the navigation P or P to the topology. And the last one we use identity law and the answer is Q. Uh, okay, this is the last example. We have to use the law of logic to prove this proposition. Okay, first we have to use distribution law. Next we have to use distribution law again. Next we have to use inverse law to change Q or negative Q to the topology and negation P or P to the top. Okay, next we have to use identity law. Next we have to use derivation of implication, and the last one we have use bind condition identity law, and the answer is P condition negation Q. Okay, that's all for me.
Mathematical terminology refers to the specific vocabulary and system of symbols used to communicate mathematical concepts, with varying degrees of precision. Unlike natural language, which can be ambiguous, mathematical terminology is designed to be exact, ensuring that a statement has only one possible logical interpretation. In mathematics, terminology acts as a shorthand for complex logical ideas. It consists of two main parts. One, vocabulary, which is words, often derived from Greek or Latin, that describes object, properties, or actions. And also a notation, which is a symbol that represents quantities, operation, or relationships. Analyze of proof. A. N is an even integer. B. N squared is an even integer. B1. N squared equals to 2k for some integer k. A1. N equals to 2a for some integer a. A2. N squared equals to bracket 2a squared. Squaring both sides of a1 equals to 4a squared equals to 2 bracket 2a squared equals to 2k, where k is some integer. Therefore, a2 is equivalent to b1. Analyze of proof. A. The right triangle RST with sides of length r and s and hypotenuse of length t. Satisfy t equals the square root of 2rs. B. The triangle RST is isosceles. B1. R equals to S. B2. R minus S equals to 0. A1. T squared equals to 2rs. From the hypothesis, t equals to square root 2rs. A2. R squared plus S squared is equal to t squared from the Pythagoras theorem. A3. When we substitute A1 into A2, we'll get R squared plus S squared equals to 2RS. A4. From A3, we could get R squared minus 2RS plus S squared equals to 0. A5. By factorizing A4, you could get bracket R minus S squared equals to 0. A6. R minus S equals to 0 when you derive it from A5. Therefore, A6 is equivalent to B2, B1 R equals to S, and B triangle RST is isosceles. Example 3. If S is an even integer and T is an odd integer, then bracket ST squared is an even integer. Your answer should have an analysis of proof and condensed proof. Analysis of proof. A. S is an even integer and T is an odd integer. B. Bracket ST squared is an even integer. B1. Bracket ST squared equals to 2k for some integer k. A1. S equals to 2r for some integer r. T equals to 2p plus 1 for some integer p. A2. ST is equals to 2r bracket 2p plus 1 and it is equals to 4rp plus 2r. A3 bracket ST squared is equals to bracket 4rp plus 2r squared, which we can get after that is 8r squared p squared plus 8r squared p plus 2r squared. And this way we can see that.
Okay, now I want to explain about the choice method. The choice method is used when the statement in the backward process contains the universal quantifier for all such statements occur frequently in the set theory. For the set theory, a set in collection of objects. If the object is in a set and collect a member or element of the set. Second, member of E, not a member of. A set is denoted by enclosing the list of its members separated by commas in set braces. A equal 2, 4, 6, and 8. And set which very large number of members or sets with infinite members can be denoted by using set order notation. Okay, now they have three how to use the choose method. First, identify the problem. Identify the problem is recognizing and clearly defining what need to be solved by analyzing given information, conditions, and goals using logic and mathematical reasoning. Number two, choose an element. Choose an element is selecting a specific item, value, or members from a given set or group based on defined rules, conditions, or logical reasoning. And lastly, conclude. Conclude is arriving at a final statement or result based on logical reasoning, evidence, and mathematical steps that have been correctly followed. Okay, now we go for example. Example 1. Set of all real numbers greater than or equal to 0 as bracket real number adds 0. Second, to check if a particular object belongs to the set or not, check if the object satisfies the defining property, which is for element of S by negative 9, not element of S. Third, sometimes part of the defining property appears to the left of as well as to the right. And a set is said to be empty if it has no members notation. Okay, for the example 2, the question is given to set S and T defined as follow. S, the number S at square negative 1 less than 0, and T, the number S negative 1 less than S less than 1. Use the choose method to prove that T subset of S. So solution is A, S equal real number S at square minus 1 less than 0, and T, the number S minus 1 less than S less than 1. B, T subset S, B1 for element T in T. T is in S. A1, choose an element, say T1 in T. B2, T1 is in S. B3, T1 square minus 1 less than 0. A2, negative 1 less than T1 less than 1. A3, T1 more than negative 1 and T1 less than 1. A4, T1 plus 1 greater than 0 and T1 minus 1 less than 0. A5, T1 plus 1, T1 minus 1 less than 0, and lastly A6, T1 square minus 1 less than 0. So the answer is A6 to B3. That's for me. Okay, the last example. The question is given to set S and T defined as follows. If S at element of R at square negative S plus 2 greater than 0, T at subset set X element or of R as less than 1 or as greater than 2, then S subset of T, ignore the condensation's proof. So the solution is A, S equal at element of R at square negative X plus 2 greater than 0. T equals S element of R X less than 1 or S greater than 2. B, S subset of T B1 for all x element s, then x element of t. A1 choose y element of s. B2 y element of t. A2 y square minus 3y plus 2 greater than 0. A3 bracket y minus 1 y minus 2 greater than 0, and F4 case 1 minus y minus 1 greater than 0 and y minus 2 greater than 0, or case 2 y minus 1 less than 0 and y total y minus 2 less than 0, and F5 y less than 1 or y greater than 2 exceeds y element of t. So the answer is exceed to B2. That's about it. Thank you.
In conclusion, this assignment has highlighted the fundamental importance of mathematical logic and proving techniques. We have established that Chapter 2 is essential for solving logical problem effectively, and Chapter 3 has equipped us with the necessary skills to identify and apply the correct proving method for specific problems. Ultimately, the process of creating this video and researching these topics has significantly enhanced our understanding and knowledge of these mathematical principles.